the task of uniquely identifying entities in text. Consider this sentence. Ford forded the ford in the Ford. This sentence has a person, an action, a shallow body of water, and a car, all named Ford. To uniquely identify each entity, you first need to identify the entities of interest. With the entities identified, you can then link them to more data on the topic. Often, this link is to a web article or entry in a knowledge base. The Ford example is complicated because which Ford to link to depends on the Ford in the question. The context in which Ford is used can help you decide if you should link the car to a car company, the body of water, the person, or the action. Together, NER and NED enable named entity linking, also called NEL. NEL is the key task for digital assistants and search engines to return the correct results. For example, if you search for news about Paris, an assistant needs to figure out if Paris means the person or the place. Spacey has tools to identify entities based on a knowledge base that you create. Now we have relationship extraction, which is the NLP task that identifies relationships between entities. This task helps with applications such as Q&A systems, digital assistants, search, and text summarization. In the example that is shown, it's easy for a human to determine that Jeff Bezos is the CEO of Amazon. To do this in NLP, you first need to identify entities by using a named entity recognizer. Then you need to determine if there is a semantic relationship between them. Three main techniques exist to determine the relationship. The first technique is rule-based. This technique defines a set of rules for the syntax and grammar to extract the relationship. These patterns look similar to X, such as Y, which could match musical instruments, such as guitars. The second is supervised. This requires a large labeled data set of relationships to learn from. Finally, there is semi-supervised. This technique uses a few labeled examples to seed the data. That data is then used to extract more relationships. Amazon Comprehend Medical provides relationship extraction that can tie information together. For example, consider the phrase left chest pain. Pain is extracted as the medical condition, with chest as the anatomical location and left as the direction. Spacey provides a set of rule-based matching, which you can use to build relationships. The final type of information extraction is event extraction. This is the process of extracting knowledge about events in text. Events can be anything from meetings to stock price changes to elections. Event extraction is challenging. An event must first be detected in the text. Then, the key event information, such as participants, location, and date, must be extracted. Consider the example. Any company announced today a 2-to-1 stock split, which will be effective on May 24, 2021 at market open. One approach would be to use pattern matching to detect the event, in this case, stock split. From there, you could find the entities detected in the sentence to find the organization. Then you could use pattern matching to look for the date and numerical values for the split. Amazon Comprehend has functionality to detect events such as bankruptcy, employment, corporate acquisition, investment, corporate merger, IPO, rights issue, secondary offering, shelf offering, tender offering, or stock split. In this section, you learned 5 different types of information extraction. Key phrase extraction finds the useful words or phrases from text. Named entity recognition identifies entities such as people's names or locations. Named entity disambiguation uniquely identifies entities in text. Relationship extraction deals with relationships between entities. And finally, event extraction is about finding events in text, such as stock splits or IPOs. In the next video, you learn about tools for information extraction. Thanks for watching. Welcome to Section 3. In this section, you look at some of the AWS services and open source tools for information extraction. Amazon Comprehend provides a number of asynchronous jobs through the API for tasks such as sentiment analysis, language detection, and topic modeling. A number of the service's capabilities are relevant for the general information extraction. First, the service can help detect textual references to entities. such as the names of people, places, and things. Next, Amazon Comprehend can help to analyze documents to detect specific types of events. Examples include mergers and bankruptcies. The service can also help to find key phrases such as good morning in a document. Amazon Comprehend can also help to analyze documents to detect personally identifiable information, called PII. This is data that could be used to identify an individual, such as an address, bank account number, or phone number. Finally, the service can parse the words in your text to show the speech syntax for each word. This can help you understand the document's content. You can run these jobs against your documents without much data preparation or knowledge of machine learning. However, you do need some knowledge of how to handle the returned data to understand and use the results. Before you can start a job, you need to prepare your data. You can store data in a single file with one document per line, or each document in its own file. Regardless, each document has a maximum size of 102,400 bytes, and it must be in UTF-8 format. You need to store the input files in a bucket in Amazon Simple Storage Service or Amazon S3. To start a job that is asynchronous, use the Start Entities Detection Job function. To manage your jobs, use the function for listing called List Entities Detection Jobs, and for describing called Describe Entities Detection Job. Once the job is complete, the results are output to the S3 bucket you specified. The example on the slide shows the output. Begin offset and end offset specify the start and end characters of the entity. Score is the confidence level that Amazon Comprehend attaches to the entity. Text is the actual entity that was found. Type indicates the type of entity that was found, such as person or location. With Amazon Comprehend, you can also train a custom entity recognizer, rather than being limited to the available entity types. If you have sufficient data to train effectively, you can identify almost any type of entity. You can provide your data to Amazon Comprehend in two ways. With annotations, you provide the location of your entities in a large number of documents so that Amazon Comprehend can train on both the entity and its context. With Entity List, you can provide limited context. This method only uses a list of the specific entities so that Amazon Comprehend can train to identify the custom entity. When using annotations to train a custom entity recognizer, you must provide annotated training data. Annotations label entities in context by associating your custom entity types with the locations where they occur in your training documents. You can provide this training data as a comma-separated values or CSV file. The slide shows 4 lines from an example training file where a person's name is the entity. The first line is Anna Carolina Silva is an engineer in the high-tech industry. So the entity for this line is Anna Carolina Silva. The table shows the annotation data for the file. The annotation has the line number, the start and end characters where the entity is found, and the type of entity. Look at the annotation for the first line, line 0. The entity Anna Carolina's name begins at character 0 and ends at character 18. Engineer is the entity type. Note that the third line from the training file isn't listed in the table. That's because the line doesn't have an entity of interest. Jorge is a judge, not an engineer or manager. Building a large annotated training document can be complex. You can use Amazon SageMaker Ground Truth to label the data set you need to train an Amazon Comprehend custom entity recognizer. Ground Truth provides built-in labeling workflows that take you step by step through tasks. The workflows also provide tools to efficiently and accurately build the annotated NER datasets required for Amazon Comprehend. The diagram on the slide shows the end-to-end process. First, you upload a set of text files to create Amazon S3. Then you create a private work team and an NER labeling job in Ground Truth. Next, the private work team labels all the text documents. When that is complete, Ground Truth creates an augmented manifest called Manifest in Amazon S3. Next, an AWS Lambda function parses the output manifest to create the annotations and documents in a CSV file, which Amazon Comprehend requires. Finally, on the Amazon Comprehend console, you launch a custom NER training job using the dataset generated in Step 4. When using an entity list for custom entity recognition, you need to supply a CSV file with only 2 columns. The first column contains the text of an entry example as it is written in the document corpus. The second column gives the entity type, which you define. The entity type must be uppercase with underscores in place of spaces. For example, senior_manager. You can train up to 25 entity types per model. The slide shows the example training data from a previous slide. Again, the entity is a person's name. The table shows the entity list for this data. Look at the first row. The first column has the entity text, Anna Carolina Silva. The second column gives the entity type, engineer. Again, the third line from the training file isn't included in the entity list. That's because the line doesn't have an entity of interest. Note that you need a minimum of 200 entity matches per entity in the entity list to train a model for custom entity recognition. Spacy features a statistical entity recognition system, which assigns labels to contiguous spans of tokens. The default train pipelines can identify a variety of named and numeric entities, including companies, locations, organizations, and products. Entity identification can only be as good as the data used to train the model. You might need to use your own labeled dataset to train the model, especially for domain-specific terms. To update an existing model, you need a few hundred to a few thousand examples. For a new category, you need a few thousand to hundreds of thousands. It can be time-consuming to create these training sets, and it requires human annotators. In the example on the slide, the code first loads a pre-trained model named EN-Core WebSM and initializes the NLP object with the text. This returns a doc object. You can iterate through the ENTS property of the doc object to display the entities. Spacy also contains a visualizer named DisplayC, which is useful for learning and troubleshooting. In this section, you learned about the information extraction capabilities that Amazon Comprehend provides. These require minimal machine learning knowledge. You also looked at how to extend the pre-trained models using your own annotations or entity list. You also learned about Spacy, which is one of many third-party packages that provide functions for IE tasks. Thanks for completing this module. In the next module, you'll learn about topic modeling. See you in the next video.
Hi, and welcome to Module 6, Introducing Topic Modeling. In this module, you'll learn about what topic modeling is, how you can do topic modeling by using the natural language processing, or NLP, tasks that you've already learned about, and 3 ways you can implement topic modeling on AWS. This module also includes 2 guided labs. The labs give you the opportunity to try out topic modeling before you move on to a challenge lab. In the challenge lab, you'll put your new skills into practice. At the end of this module, you should be able to understand the use cases for topic modeling, describe the steps for topic modeling, use Amazon Comprehend to implement a topic modeling solution, evaluate machine learning, or ML, algorithms used in NLP for topic modeling, and create a solution to a topic modeling business problem. Okay, it's time to get started. In this section, you take a look at what topic modeling is. Topic modeling is the process of extracting topics from a large collection of documents. Topic modeling is an unsupervised machine learning model that scans a set of documents to detect word and phrase patterns. These words and patterns are grouped into clusters that best characterize the documents. In the diagram, you can see 2 possible topics identified, Topic A and Topic B. Topic A contains the words singer, lead, drummer, and beat. Topic B contains steel, aluminum, casting, and lead. Based on the topics, Topic A might be music or bands. Topic B might be about metallurgy or manufacturing. A key note is the topics are represented by a collection of related words or phrases. Topic modeling doesn't usually identify the topics themselves. Human intervention is often required for that. It's also worth noting that the topics might not be the same as what a human would identify. Topic modeling has many practical use cases. It can help with document classification based on the topics detected. You can use topic modeling to automatically tag content by using tags mapped to a set of topics. Another use is document summarization using the topics found in the document. You can use topic modeling to retrieve information using topics. And a final example is recommending content based on topic similarities. You can also use topic modeling as a feature engineering step for downstream text-related machine learning tasks. In this section, you looked at what topic modeling is and some of the use cases for topic modeling. In the next section, you will look at how to approach topic modeling. Thanks for watching. In this section, you'll take a look at approaches to topic modeling. Documents can contain a mixture of topics. Topic modeling tries to extract words that are relevant in a document. Documents that share common terms share a topic. Note that documents might contain more than one topic. Two documents with similar topics won't have the exact same content. However, overall, you would expect these documents to more frequently share a subset of words compared to documents from a different topic mix. In Module 3, you learned about term frequency inverse document frequency, known as TF-IDF. This is a way to extract key terms that are important to the document. You can use this method on a set of documents to extract those terms. Then, group documents with similar terms together. You can also visualize the words as vectors. When terms share the same vector space, it indicates that they are related. Topic modeling simply tries to identify which terms belong together. As with any NLP task, it is helpful to understand how the model works so that you can prepare the data. Because the models look for common words across documents, you might want to take a number of key steps. First, clean the data. This includes removing HTML tags, markup, numerical data, and whitespace to have a better set of text to work with. Next, remove stop words. These tend not to add value in these types of NLP tasks. Third, limitize the data. This is important because you want to find groups of words that are common across documents. Limitization can help reduce the number of word variations needed. Finally, vectorize or tokenize the documents, depending on the requirements of the algorithm that you're using. In this section, you looked at a high-level approach to topic modeling. You also reviewed some of the key processing steps required to prepare your data, such as cleaning your data, removing stop words, lemmatization, and vectorizing or tokenizing your text. Thanks for watching. In the next video, you'll look at how to implement topic modeling. In this section, you learn about options to implement topic modeling. You can use Amazon Comprehend to examine a collection of documents to determine common topics. For best results, you need to use at least 1,000 documents in each topic modeling job. With Amazon Comprehend, you do not need to train a model or pre-process your data. To get started, create one or more UTF text files in an Amazon Simple Storage service known as Amazon S3. Then, create an Amazon Comprehend topic modeling job. When a job is complete, you have two output files. The first, topicterms.csv, contains a list of all the topics and the top terms for each topic according to their weights. The weight represents a probability distribution over the words in a given topic. Amazon Comprehend only returns the top 10 words for each topic. This means the weights won't add up to 1 unless you have fewer than 10 terms. The 10 terms should be enough for you to determine whether a topic makes sense. Amazon Comprehend can detect up to 100 topics per job, but you can specify how many you want to find based on your domain knowledge. The second file is the topics.csv file. This lists the documents associated with the topic and the proportion of the document that is concerned with the topic. Note that the names of the topics are not given. Naming the topics is a human task. Amazon SageMaker contains two built-in algorithms to extract topics from text. The first is latent directlet allocation, or LDA. LDA is an unsupervised learning algorithm that attempts to describe a set of documents as a mixture of distinct topics. Because this algorithm is unsupervised, the topics are not specified up front. The topics might not line up with how a human would categorize documents. The topics themselves are learned as a probability distribution over the words that occur in each document. Each document, in turn, is described as a mixture of topics. As an example, consider a set of documents that only contain the words eat, sleep, play, meow, and bark. LDA might produce the two topics shown in the table. Topic 1 might be about cats, who are likely to meow and sleep. And topic 2 might be about dogs who play and bark. To train an LDA model, you need a set of documents. Pre-process these documents appropriately, depending on your documents. The typical steps you would take are to clean the text, remove stop words, remove non-text, and perform lemmatization. Next, tokenize the text by using a bag of words, or BOW, or some other tokenizer. Note that lemmatization significantly increases algorithm performance and accuracy. To train, you need to supply the data on the train channel. You can optionally supply test data, which the final model scores to provide the metric test PWLL. PWLL is the per-word log likelihood on the test dataset. This metric represents the likelihood that the learned LDA model accurately describes the test dataset. The goal is to maximize this value. The data can be in a record IO wrapped protobuf or .csv file. You must supply a few hyperparameters. The first is num topics, which is the number of topics for LDA to find within the data. The second is feature dim. This is the size of the vocabulary of the input document corpus. The final hyperparameter is mini batch size, which is the total number of documents in the input document corpus. LDA only supports single CPU training. The output of the training job is a model that can identify topics that are discovered from the input corpus. To infer from the model, you must deploy the model. Once deployed, you should run your documents to infer through the same pre-processing pipeline before calling the model. The output of the model is a Python dictionary that contains predictions with each topic mixture referring to an input document. Each element of the topic mixture corresponds to a topic learned when the original model was trained. In the example shown, the first document is most likely about topics 2 and 5. The second document is likely about topics 2 and possibly 4, depending on your threshold. Thanks for watching. In the next video, you'll learn about the Neural Topic Model, or NTM, algorithm. Welcome. In this video, you'll learn about the Neural Topic Model algorithm, also called the NTM algorithm. You'll also learn how to choose between training a model and using Amazon Comprehend for topic modeling. NTM is the second Amazon SageMaker algorithm. It's another unsupervised learning algorithm that organizes documents into topics that contain word groupings based on statistical distribution. Again, because it's unsupervised, the topics are not specified up front. You only specify the number of topics to find. The discovered topics might not align with how a human with domain knowledge would categorize them. NTM and latent directlet allocation, LDA, are distinct algorithms. Therefore, expect them to produce different results. The NTM algorithm requires similar processing to LDA. You must remove stop words, remove non-text, lemmatize the data, and tokenize the data. NTM supports 4 channels: train, validation, test, and auxiliary. Train is the only required channel, and you should already be familiar with the validation and test channels. However, auxiliary is likely new to you. The auxiliary channel is used to supply a text file that contains vocabulary. When you supply the vocabulary file, users are able to see the top words in each topic instead of only the integer IDs. This is similar to the output from Amazon Comprehend. In addition, NTM can use the vocabulary file to compute the Word Embedding Topic Coherence, or WTEC score. This new metric is displayed in the log that captures similarity among the topic words in each document. The vocabulary file is a plain text file with a content type of text/plain. Each line in the file contains a single word corresponding to the integer IDs provided in the data. This file must be named vocab.txt and be UTF-8 encoded. You must supply a number of hyperparameters. The first is num topics, which is the number of topics for NTM to find within the data. The maximum is 1 million. The second hyperparameter is feature dim. This is the size of the vocabulary of the input document corpus. The metric used for tuning is validation total loss. It is the sum of the reconstruction loss and Kullback-Leibler divergence. When tuning, try to minimize this value. NTM supports both GPU and CPU instance types, with GPUs recommended. With a trained model, you must deploy it to perform inferences. We recommend that you pre-process your documents with the same pipeline. The results are almost identical to the LDA results, except instead of the topic mixture, you get the topic weights. They're essentially the same and indicate which documents belong to which topics. As with any machine learning problem, choosing the right algorithm is a function of your business goal. To choose between LDA and NTM, consider two metrics: perplexity and coherence. Perplexity is a measure of the likelihood that a word will appear in a topic. A lower perplexity score indicates that you are more likely to be able to generalize the model. However, if you rely on perplexity alone to select an algorithm, it might not align with how a human would categorize the topics. Coherence is another metric you can use to help overcome the problem of relying on perplexity. With coherence, you calculate the average or median similarity of pairs of words in a defined set of words in a topic. When you minimize perplexity and maximize coherence, you are more likely to optimize the model that you use for topic modeling. With 3 choices for topic modeling, you might be wondering when to use each. Amazon Comprehend provides a fully managed service that you can use quickly without any data preparation. This option is good for projects when you need quick results or are working within tight deadlines. Built-in algorithms such as NTM and LDA require more work up front to train the models. You must pre-process the data and tune the models, which can take time. However, the advantage is models that can use domain-specific vocabulary. You might also need to use these algorithms for compliance reasons, where you need detailed audits of data access and processing. LDA and NTM can give you different results based on the same data set. LDA is faster than other implementations, and NTM can use multiple GPUs. Try both algorithms to see which gives you the best results. In this section, you looked at 3 different ways to implement topic modeling. Amazon Comprehend provides a fully managed service that requires little processing. LDA and NTM are both Amazon SageMaker algorithms and require training before you can perform inferences. You also looked at some trade-offs among the 3 options. Thanks for completing this module. In the next module, you'll learn how to use AWS services to transcribe, translate, and convert text into audio output. See you in the next video.